Modern artificial intelligence is judged by isolated episodes of success. We see a model pass a benchmark or a demonstration succeed under controlled conditions, and we assume the system is competent. But this performance is often a temporary artifact of a static environment. A successful benchmark proves capability is possible. It does not prove that that capability can survive the entropy of actual operations. In production, the conditions of that original success disappear. Inputs arrive and alter forms, business definitions drift, and the assumptions that held the demonstration together begin to fail as the environment changes. When a key reviewer leaves an organization, the baseline judgment of the system often leaves with them. Temporary exceptions become permanent habits, and the discipline required to maintain the model's performance degrades. Tooling shifts create further instability. Upgrading a model or replacing a tool interface can instantly sever the connections that allowed the previous version to function reliably. These failures indicate that while the model may be intelligent, the organization lacks operational continuity. Judgment cannot be preserved, transferred, or improved if it depends entirely on a single, fragile configuration. There is a common misconception that placing an intelligent model into a standard workflow solves this. If we chain prompts and tools together in a sequence, we assume we have built a system. Most workflows are represented as directed acyclic graphs, a linear sequence of boxes and arrows. This structure is designed for coordination, tracking an input as it moves through various tasks to become an output. While useful for simple data processing, this representation is too shallow for governing autonomous systems. An AI agent can follow every step in a sequence, while the underlying context and constraints completely evaporate. The sequence remains intact, but the meaning behind the work is lost. This creates mere motion. The system accelerates, producing a high volume of tool calls, reports, and alerts that fail to move the organization closer to its objective. Effective progress, by contrast, requires a structural change. A step only matters if it reduces material uncertainty, clarifies an active constraint, or excludes an invalid path. To achieve this, organizations must move beyond fixed task sequences and adopt a control layer that governs the state of the problem itself. This framework, known as the energetic paradigm, treats a workflow as a governed system of state transitions. Every step must produce a transition in the state of the problem. If an action doesn't change the uncertainty, the authority, or the constraints of the system, it is an unproductive use of compute. The logic of this paradigm is captured in a state transition formula. It defines the next state, xt plus 1, as a function of 5 distinct variables. The transition begins with the current workflow state, xt, and the authorized action, at. That action is only valid if it is supported by the relevant evidential condition, et. This choice is then physically bounded by CT, the active constraints that define what the system is allowed to do. Finally, MT represents the memory that shapes the future trajectory, ensuring that past lessons influence current transitions. This formula shifts the focus from what happens next to a more rigorous requirement, identifying the specific structural change that justifies the next action. In many AI systems, context is passive. We provide the model with documents, policies, and records, and hope the model applies them correctly. This leads to failure. A model may process a conditional approval, but summarize it as an unconditional decision because the condition lacked causal force. Without an active structure, outdated rules and descriptive statements are frequently mistaken for mandatory constraints, leading the system into invalid states. This paradigm differentiates context by its functional role. One piece of information might be a revisable hypothesis, while another is a hard stopping condition.
If a critical condition is missing, the workflow is physically blocked. It cannot proceed based on stylistic confidence alone. It requires valid evidence. This active constraint architecture prunes invalid paths, ensuring the system only explores routes that produce verified progress toward the target state. Causal force is the true metric of context. Whether the model has read the text is secondary to whether that information exerts control over the workflow's behavior. Memory requires governance to be effective. Too little memory produces organizational amnesia, where the system is forced to repeat analysis and pay for the same errors multiple times. Too much indiscriminate memory creates pollution. The system becomes bogged down by stale rules and local exceptions that are no longer relevant to the current environment. Operational memory is only valuable when it acts as a historical structure that actively modifies future choices. Because conditions change, memory must have decay. Its influence must be adjusted as data drifts or policies are revised, ensuring the system isn't governed by an obsolete past. This leads to the distinction between correcting a mistake and repairing a system. If an AI generates a flawed summary and a human fixes the text, that is a correction. It fixes today's output, but as shown on the left, it does nothing to prevent the same error from recurring in the next execution. A structural repair, on the right, uses the failure as diagnostic data. It asks why the constraint lost force or why the evidence was weakened during the handoff. The repair is complete only when the workflow's future state space has changed, making it physically impossible for the system to repeat that specific failure. A failure that does not change the next workflow is just history. It only becomes learning when it reshapes future operation. Human involvement is often treated as a ceremonial checkpoint. We put a review box at the end of the workflow and ask for a signature. This often fails because the reviewer lacks the decisive evidence needed to make a judgment. They approve the result because the process expects them to finish the task. We should instead treat review as a state transition. A reviewer's input should be capable of changing the trust granted to the result, altering the next route, or updating the memory retained by the system. This requires a dynamic allocation of authority. Instead of static roles, the power to act is distributed among humans, models, and tools based on the current state. If an action is easily reversible, the model is granted high autonomy to move the workflow forward. But when consequences become irreversible, the model's authority contracts, making recommendations while human judgment expands to control the transition. This dynamic shifting prevents the bottlenecks of excessive human insertion, while avoiding the risks of machine autonomy separated from consequence. Governance functions by determining specific authorization at a given state, rather than relying on generic definitions of responsibility. There is a concern that this level of governance creates procedural rigidity, eliminating the flexibility required for artificial intelligence to be useful. However, this framework enables adaptation by defining a stable governance envelope. It does not enforce a single fixed route. Inside this envelope, the system is free to explore candidate paths and revise its approach, provided it preserves its objective and adheres to active constraints. By institutionalizing path, authority, and trust governance, we move from episodic model performances to durable organizational intelligence. The result is a system that can adapt its route to bypass obstacles while maintaining the structural cohesion required to protect its purpose. Institutional intelligence exists when judgment can be reproduced without depending on the presence of a specific person or model instance. By governing workflows as state transition systems, we ensure that intelligence can return, repair itself, and persist across time.